Welcome back. I'm Robert.
And I'm still James.
In this video, we are doing determinants and inverses.
Yeah, that. Before we begin, it's important to remember that only square matrices have inverses or determinants.
So to start, we'll begin with 2x2 matrices. To work out the determinant of a 2x2 matrix of the form ABCD, the determinant is simply AD minus BC.
So in this example, the determinant of the matrix 1, 2, 3, 4 is just 1 times 4 minus 2 times 3.
Next, to find the inverse of a 2x2 matrix, you swap A and D, change the signs of B and C, then divide everything by the determinant. So, trying to find the inverse of the matrix 1, 2, 3, 4, we swap 1 and 4, and 2 and 3 become minus 2 and minus 3, and then we divide all the terms by minus 2, the determinant we just worked out.
Two things to note: there is no inverse for a matrix if its determinant is 0, and any matrix multiplied by its inverse gives the identity matrix.
Now for matrices larger than 2x2. Let's begin with some definitions. Mij of A is called the minor of A and is the determinant of the n-1 by n-1 matrix after deleting row I and column j. The cofactor of matrix A is Cij of A, which is equal to minus 1 to the power of I plus j multiplied by the minor at ij.
And I got none of that.
Let's just go through the example. With A as shown, the minor at 1, 1 is equal to the determinant of 2, 3, 2, 3, as we have deleted the first row and first column of A, which, as we can see, is 0. The cofactor at 1, 1 is equal to minus 1 to the power of 1 plus 1, multiplied by 0, which is also 0.
A piece of matrix notation to be aware of is the determinant of A can be written as A in modulus lines.
The determinant of A is equal to the sum of each element in a chosen row or column, multiplied by the cofactor of that element. The following is an example of this. If we choose to use row 1, we can work out the determinant by following the method above.
That's a bit of a faff though.
Yes, but if we choose row 3, it is a lot easier and quicker to work it out.
So, it is often easier to choose the row or column with the most zeros?
Yes, as you have less things to add together. If A is an upper triangular, lower triangular, or diagonal matrix, this is even easier, as the determinant is just the product of all Aij, where I is equal to j.
So just the product of the diagonals.
Because of this, the determinant of the identity matrix is 1 for every identity matrix.
A useful note is that a matrix with a row or column entirely made of zeros will have a determinant of 0.
Now on to the inverses. If the inverses of two matrices A and B exist, then the inverse of A times B is the same as the inverse of B times the inverse of A.
To calculate the inverse of an n by n matrix A, we put the matrix A next to the identity matrix of the same size. We then mess about with both of them.
We perform a series of row operations on the two of them simultaneously until the matrix A has become the identity matrix. The matrix where the identity was when we began is the inverse of the matrix A.
Yeah, alright, I was getting to that bit. For an example, consider the following matrix A. Putting it beside the identity matrix, the first transformation we perform is to take 2 times the first row from the second row. Then we take 3 times the first row from the third row. Then we finally take 2 times the third row from the first row. A has become the identity matrix, and the identity has become the inverse of A. And there we go. That's the determinants and inverses of matrices.
Thank you for watching.
See you around.